This video is about all things radicals. So in this video, I'll go over what radicals are, how not to and how to combine them. I'll show you how to simplify them, and then we will end with how to rationalize denominators with radicals. So last class you explored the relationship between rational exponents and radicals, like this. You saw problems like this, like the square root of 7 is the same thing as 7 to the 1/2. Or the 4th root of z cubed is the same thing as z to the 3/4. I want to define more exactly what a radical is for you. So for a positive integer, n greater than or equal to 2, and a real number b, we can have n root b, which is what we call nth root of b. So this is called a radical, and the radical value, or index we might call it, is the n value. And the number inside of the root is called the radicand. And I think that you know what a radical is and what we're supposed to do with it. So if I had the square root of 4, what this is telling me is there's some number that if I multiply it by itself twice, that I get the number 4. Because anytime we have a radical without a number here, without a radical value, it's assumed the number 2. So this is saying what number times itself equals 4. And you all know that that's 2. Or maybe we have the 4th root of 81. So this is saying there's some number times itself 4 times that equals 81. And that number is 3, because 3 times 3 is 9, times 3 is 27, times 3 is 81. Or lastly, we might see something like this, which is saying there's some number times itself 3 times that equals -8. And that number is -2, because -2 times -2 is 4, times -2 is -8. So you know what a radical is, and there are ways that we can combine radicals. So we can multiply radicals really easily, like we can multiply radicals root 5 times root 2, and we just multiply the radicand to get root 10. We can also easily divide radicals if they're single terms. Like we might have the cube root of 8 over 27, which is also the same thing as the cube root of 8 divided by the cube root of 27. And since I can find those values pretty easily, because the cube root of 8 is 2 and the cube root of 27 is 3, I just get 2/3. But adding and subtracting radicals is a little bit different, because we need to make sure the radicals are like terms before combining them. So in other words, if we had root 4 plus 3 root 4, because these have the same radicand, we can just add them as if they were like terms. So there's one of these, there's like an invisible 1 right here, and we just do 1 plus 3, which is 4, and it's 4 root 4. And actually we can simplify that farther, because the square root of 4 is 2, so this would end up being 4 times 2, which is 8. But if we had 2 root 11 minus 3 root 11 plus 11 root 2, there's 2 of these terms that are like terms and 1 that is not. So the root 11s have the same radicand, and those can be combined. but root 2 cannot be combined with those. So to simplify this, we've got 2 minus 3, which is negative 1, and I can just write it as negative root 11. And then 11 root 2 is just going to hang out by itself because it can't combine with anything. And this is really similar to just x and y's. If I had 2x minus 3x plus 11y, you could only combine the x's and not the y. Just like other concepts in algebra, we can simplify radicals. So we can put radicals in simplest form, meaning there's no other factors that can be taken out of the radical. Some rules for simplifying radical is that no factors can be pulled out of the radicand. That there's no denominator. There's no radical in the denominator. And that the radical does not have any fractions. So here are some examples of how to simplify radicals. Say we had square root of x to the third. Well, you all know that x to the third is the same thing as x times x times x. So since this is a radical value of 2 here, I'm going to be looking for pairs of 2. So here I have a pair of 2. That means I can take one of the x's out, or this pair of x's out, and I would be left with x on the outside, and then on the inside of the radical, we just have this lonely x. Let's look at this example, cube root of x to the sixth. So I'm looking for pairs of 3. Well, x to the sixth is x times x times x times x times x times x, right? Well, I have 2 pairs of 3x's. So that means I can pull each of these out. Those go out and this go out. And then when you pull those factors out, you're going to multiply them together. So I'm left with x squared. Let's look at an example where we have a radical in the denominator. So right here I have square root of x in the denominator, and that's against one of the rules for simplifying radicals. You can't have that in there. So the way that you're going to get rid of it is you're going to multiply the top of the fraction and the bottom of the fraction by that same square root to get rid of it. Because on the denominator on the bottom, the square root of x times the square root of x is just x itself. Let's look at it this way. You can multiply the radicands together. You get x squared when you multiply square root of x times the square root of x. So the square root of x squared is just x. And then in the numerator, we have the square root of x, and that's okay because the numerator can have a radical, just the denominator cannot. And then lastly, let's look at this number right here, the square root of 3/5. If we want to simplify this, this goes against the rules where there's a fraction inside the radical. So we kind of have to think about it like this, a radical on top and a radical on bottom. And we want to get rid of the radical on the bottom because that's it breaking another rule. So the bottom, square root of 5 times the square root of 5 is just 5. And then on the top, square root of 3 times the square root of 5 is square root of 15. So that one is simplified. So the last 2 examples I showed you on the previous slide were actually examples of rationalizing a denominator. These were single radicals in the denominator, but sometimes we may have 2 terms in the denominator like this. And if we simply multiplied that by the square root of 2, we wouldn't get rid of the radical that's in the denominator. So we have to do something different. What we need to do is we have to multiply the denominator by its conjugate. Let me write that over here for you, because it's really good to use the correct language. So we have to multiply it by the conjugate. The conjugate is the same expression, but you're changing the sign. So the conjugate of 3 minus root 2 is 3 plus root 2. If the original fraction it was 3 plus root 2, its conjugate would be 3 minus root 2. So you're going to multiply the top and bottom by the conjugate, and then you're going to simplify by distributing the 5 to everything in the numerator. So you get 15 plus 5 root 2. And then in the denominator, you have the difference of squares. So it's a binomial times a binomial. We could FOIL it, but that's kind of a waste of our time at this point in our math career. And with this pattern, we can multiply these first together to get 9, and then these last together to be 2, or minus 2, because the square root of 2 times the square root of 2 is 2. And the middle terms cancel each other out. So we would just simplify at this point over here, 15 plus 5 root 2 over 7. And that is it for this video. Have a great one, and let me know if you have any questions.